Hey, welcome back to Interconnects. On this interview, we're bringing one that I've hinted at for a while, which is interviewing some of the other leads on the OLMo team at AI2. So essentially, this covers the story of OLMo from its early days, where we got our compute, kind of our path to stability, and some failed runs along the way, the role of OLMo in the broader AI ecosystem, and really just a very long tail of technical details and decision making and considerations that you have when actually training language models that you're trying to have at the frontier of performance relative to peers like Llama, etc. This is a fun one. There's less post-training than normal because this is me interviewing some other co-leads at the Allen Institute for AI. So there's three people in addition to me, which is Dirk Groeneveld, who is the lead of training, handles most of the engineering, Kyle Lowe and Luca Soldaini, who are the data leads. So we have a pre-training engineering lead and two data leads with me, who has done a lot of the post-training. This is just a part of the team, and I hope you enjoy this one. We can do more of these, and bear with the fact that I'm still expanding my podcasting tech equipment. But I think the audio is definitely good enough, and enjoy this episode with me, Kyle, Dirk, and Luca. Hey everyone, welcome to the AI2 office. We're finally talking more about some of our OLMo things. Too much work to do to actually get all the information we want to share out into the world. So I'm here with Dirk, Kyle, and Luca. You can also talk so people identify your voices, so people are not all on video.
Hi, I'm Dirk. I am the lead of the pre-training part of OLMo.
Hi, I'm Kyle. I work on data.
Hello, Luca. Also work on data with Kyle.
Okay, so I'm gonna make you go through some of the story of OLMo to start, and then just get into as many nerdy details until we get tired of OLMo 2, which, in my state, this will probably be mostly about pre-training. You can ask me post-training questions as well, but I'm not going to sit here and be like, ask myself questions that I don't have to answer, because that is an absolutely ridiculous
You
thing.
can ask yourself one question.
Okay.
One question.
It's like, why should post-training be all the compute? But I wasn't here for when OLMo actually started, so I think it'd be good to tell people, broadly, what AI2 was like at the time, what language modeling was like at the time, and why this may or may not have been risky.
Yeah, you should probably give this.
Yeah. I think it all started in the fall of 2022, right?
Mm-hmm.
We were talking to AMD at the time about some sort of collaboration. We're scoping out some stuff, and at the time we wanted to take the Bloom model and put 300 billion extra tokens in. And we wrote up a proposal and we sent it to AMD, and it disappeared into a black hole, and we never heard from it again. And then ChatGPT came out a couple months after that, and suddenly everybody was very excited. And maybe 1 month after that, AMD came back to us and said, "Now let's do it." And that kicked off a very busy period for us. At least the three of us were involved at the time, plus some more people. Trying to scope out exactly what the project would be. Putting 300 billion tokens into Bloom wasn't that cool anymore. The field had moved on, so we needed to find something else that would work both for us and for AMD. And that's exactly what we did. We figured it out. We figured out who would be on the team, how exactly to do it, where to get the data from, all of that stuff, and then started working on it.
I think I was looking it up, and the official birthday of OLMo is February 2nd, 2023. That's when we had like a big sort of half-day summit, workshop, I don't know, a bunch of researchers self-organized, a long discussion, a conversation with maybe like 40, 50 of us, tried to scope down a potential language model project at AI2.
Yeah, it was also extremely bottom up because we were all like it was not on anyone's radar. Everyone was working on different projects that we had promised for the end of the year. This was very much just like a side gig for us. We had no compute other than this mysterious AMD GPUs that just came I was like, oh, it's possible. And everyone was just like, yeah, I'll work on this on the side. Let's just start hacking together some stuff.
How far along the line until you decided on 7B? Like, were these things obvious at the time?
I think the sizes were Llama sizes.
Yeah.
So we
Yeah.
started with 7 because 7 was the smallest Llama size. This is Llama 1.
Yeah, Llama 1 was like first for a couple months
Yeah.
of 2023.
Yeah, we started scoping before Llama 1, and then when Llama 1 came out, it made sense to have a configuration that was just sort of close to what they were doing. So it's not too much reinventing. I think 7 was the obvious size there.
Yeah.
Yeah, I mean, I think the original scope was recreate Llama 1, which would be a 7B at 1.4 trillion tokens.
Were we staring
With
at OPT?
completely open data.
We were staring at OPT also, right? During around that time.
For inspiration
Yeah.
and for what not to do in many
Yeah.
cases.
Was OPT even like in the many tokens regime, or was that still like when people did Bloom
OPT
models and it was less?
I think OPT and Bloom were not overtrained. I think they were both a scope to Chinchilla. They both had extensive logs, and so they were very useful because both of them have hundreds of pages of like whatever can go wrong during pre-training.
Yeah, I mean, OPT was amazing as a resource for figuring out, we knew nothing, so we needed to know what's important and
Yeah, I
which
remember
pitfalls
there's
to avoid and so on.
There's that, like Susan has this talk on the perils of training OPT.
Yeah.
I mean, it's like one of the original ones.
I always feel it's kind of a shame because the OPT models are not very good, but they were first. Like, they figured all that stuff out for the first time. I have huge amounts of respect for that.
And was the like open source angle a thing at AI2 at the time? Or like had you already identified that there was no open pre-trained data sets for these models?
There definitely wasn't any open pre-trained datasets. I think we were basically looking at the Gopher paper that had most documentation, and then Llama 1 had enough documentation about what data sources they're using, where we were like, okay, let's try to reconstruct what it was. And I think roughly around the same time, Red Pajama V1,
Yes.
and then shortly after was like Falcon, the first Falcon. Like we were all kind of concurrent works at the time, but basically starting from, I don't know, grab Common Crawl, grab a bunch of sources to try our best.
If anything, like we had conversation of like, there was like, boy, it would be good if we didn't have to do the data. This would be one fewer thing to do. But at the time, like even when Falcon dropped, they released like a small preview that wouldn't match like the token budget that we wanted for a training run. So it was not even like, it was good work. Like, oh, maybe we just switch to this one, and then we quickly realized not big enough for the 2 trillion token. I think it was like maybe
600 billion.
Yeah, close to that.
I mean, we did the C4 data set way before any of this. And so my first idea for how to do data was to just run C4, but on all the Common Crawl dumps instead of just whatever the most recent one was at the time.
Yeah.
And I actually started writing a repo for that, but then ended up not doing
This
that.
is the C5 repo.
Yeah.
C4 is set of data cleaning practices.
Yes,
It's exactly a re-implementation of C4 for it such that it would run on slightly different hardware with more dumps, and that was going to be the entire story until we found we could do better.
Yeah, and for general timelining, I joined pretty much like almost 7B was I think mostly done training or wrapping up pre-training, and the like instruction tuning at the time was like basic SFT with a sprinkle of DPO.
Yeah.
So I think a lot of that story gets compressed. Like I'm guessing the actual pre-training happened in like the second half of the year mostly. So it's a lot of prep to get a language modeling system to exist.
Yeah, I think we handed off V1 of Llama. So the data set that we used for pre-training is like end of June, I think, 2023.
Grab Common Crawl end of March.
Yeah,
So
all the source acquisition was March, April, mostly March, and then a few months there.
If someone wants to do the same thing today, which is like we should train a language model, how much faster would it be to like? Is OLMo actually making that much of it? Like, would it be a week with OLMo stuff now, or would it still take a lot of time to spin this up?
I think if you wanna train exactly on OLMo data, data it's much faster. Training, I think it requires a little bit more finesse, and Dirk can say more.
Yeah, I mean, if someone gives you a cluster to run on, just figuring out the mechanics of getting your thing to run, just so setting all the environment variables and having the drivers loaded and so on, it might take you a week or so if you've done that kind of thing before.
So that's very different.
But you can take a trainer that already works and just use it.
It really depends like where you start. It's like if you're spinning up your cluster from scratch, then you acquire the hardware, then that hardware has burning periods. So the first 3 months, stuff will fail, but that has nothing to do with the model itself. It's just your hardware is also brand new.
Yeah, I mean, I am eternally grateful for AMD for giving us the compute to get started, but it was kind of difficult to run on.
What was the exact amount of compute? I think when I arrived, that wasn't even what we were using. Whereas like Lumi discussions and
The original amount of compute was 2 million hours on Lumi.
so what?
So 2 million GPU hours. We're training way bigger now than that.
Yeah, so I think I did the math recently. It's like the order of 1 million hours is if you do 1,000 GPUs concurrently, like 20 days.
I don't have that math in the top of my head, but the first end-to-end run for the 7B that we did took 35 days. We can now train that same model again in 3 days. So things have changed a lot since then.
Yeah, I pulled some rough stats for OLMo too. Anyways, 7 and 13, just the final runs was a little bit over 5 million GPU hours combined. And then we have roughly 5 million GPU hours worth of experiments.
These are A100 hours.
H100 hours.
I'd be surprised if that was the case.
This includes
Too high or too
I have
low?
to do some. It's way too high.
It's like, how do you account for overhead then?
Oh, combined.
It's combined. Some of them plus the ultimate training.
They're also not using the new core code base.
No.
Yeah, but I'm just thinking, if it's, let's say, conservatively 7,000 tokens per second, 4 months on 1,000 GPUs.
Busted
Calculations. We'll go and track this number down. I think it's interesting. It's like what percentage?
Fact check right there.
What is the like percentage of improvement still? Like how much of OLMo 2 being better is just by the compute being more stable, just by doing more experiments, and that lets you test things like stability and just get the ducks in a row, rather than like the data being so much better. It's an impossible question.
It was like, the tricky part with using the AMD hardware at the time, specifically that cluster was being brought up online at the same time as we were experimenting with it. So we were helping that cluster being set up. So it's because of that. There's a lot of things that where we had to second guess ourselves whether that was an issue with on our side, on the hardware side.
Isn't this always going to be an issue with new GPUs coming into the world? Does Microsoft plug in OpenAI's GPUs and they just work?
I think it was, yeah. It's always tricky. It's a combination of like getting both new GPUs from at the time AMD was a relatively new vendor, plus the cluster itself being new. So it's like stacking, risky things on top of each other. In a way that it's like, if your cluster is solid, that the GPUs are brand new, well, the network is not going to cause issues. But if the cluster is new and the GPUs are new, who knows where the problem sits?
Yeah, we'll go down the whole stability rabbit hole. Dirk, how close are you to a number?
5 trillion tokens at 7,000 tokens per second, which is what we get for the 7B,
Yep.
more or less,
Yep.
over the long run of the time, is only about 200,000 hours on an H100. So that first estimate was way off.
It was Check the top. I think maybe my memory was Falcon. Maybe my thing was
That's not why you got
500K.
it. This is why I have this laptop here. What was your number?
Oh no, I was misremembering. Okay, my database calculator is 500K. But I remember flying.
500K is a lot.
Yeah.
So it's like from the first AMD grant of a few million CPU hours on AMD to what we have today. It's like it's gone from multiple million AMD hours to training a model for 5 times the tokens in half the GPU hours.
That's right. Yeah.
Like, where do we get these improvements from?
I mean, the biggest one is that the MI250 that Lumi has on, like the MI250 is the AMD GPU that Lumi has, is of the A100 era.
Yeah.
It's comparable to an A100 in price and capacity, but now we train on H100s, and they're just
What percentage of tokens
it's just a newer GPU.
Yeah, what percentage of tokens in OLMo 1 code versus OLMo 2 code are lost at like a 7B, so a scale that we're reliable on, are lost to spikes? Like, was OLMo 1 losing a reasonable amount of tokens to spiking?
That's impossible to estimate, because there's so many other differences at the same time between OLMo 1 and OLMo 2.
Can you summarize the architecture differences? There's a list in the paper. Like, we don't have to be exhaustive.
That's going to be a lot of stuff. The biggest difference is the init. So I guess now we're getting into what did we actually discover.
These are some audience questions. Finbar, who you might know, specifically asked, like, how do you arrive at n of like 0.02 init? And I'm like, I don't know.
That particular init is the default in Megatron. And the init that we had in OLMo 1 was just trying to be too clever. We stole that init from OpenLM, and they took it from somewhere else, actually. And I don't remember what the original source is.
What is the actual decision making on a init that's too clever? You like think that you can get a better learning region by bundling with something?
We tried it. We ran it for 100 billion, 200 billion tokens, and we looked at which one is better. And scaled init is absolutely better for a long time. So scaled init is the original, it's the OLMo 1 init. Works better for a long time. You have to train for a really long time before you see it come apart. 2 trillion tokens for a 7B model. And then things get a little dicey. So this is why, we used it for OLMo 1. Because it looks quite good for a long time.
Which of our OLMo models did we figure out that the init we needed to change? Because we did a few through the year.
We tried that same init with a 70B model. And that did not work. That model stalled out around 1.3 trillion, 1.4 trillion, something like that. Which gets at the heart of the stability investigation. So I think that was one of the audience questions, right? And how do we even go about the stability investigation?
Yeah.
So starting from the point of we're training the 70B and it's not working anymore, what do we do? The first step was to identify the issues that we see in the metrics and see them in a smaller model. And the 2 issues we saw were lots of spikes, that we call them fast spikes, so the model recovers quickly, but they just happen more and more the longer you keep training. And at some point, even the fast spikes kill you. And the other thing was a growth in grad norm. It seemed very much that the 70B would always start blowing up once the grad norm got to 0.4. Regardless of what intervention we did, it would get a little bit further, and then as soon as we hit 0.4 grad norm, it would blow up again.
So you lower the learning rate and then it goes up again.
So fortunately, yeah, we would do things like that. Increase the batch size, change the rate decay, blah, blah, blah. But quickly it gets back to 0.4 and then goes up again. So fortunately, both of those phenomena also appear at the 7B. Even though the 7B trains fine, it has both of those traits. So we decided to focus on those 2 because it's too expensive to try all these experiments at 70B. But these are 2 things we could fix at 7B and then see how it goes. So that was the first step. And now we have a metric where we can pretty quickly, within 12 hours or so, do a run, find out if our numbers are better, and then change something and do it again. And the second component was we took another model that successfully trained that didn't show these issues, that didn't show the slow grad norm growth, and it didn't show the spikes either. and we ablated against that. So that was the LM360 Ember model. They're like OLMo very open, so we could take their data, we could take their setup, and look at it in great detail. And we basically tried things one by one, sometimes 2 by 2 or so to not run too many ablations, but we tried things until we got to a stable setup. There are some other insights. At the time, I was really into the Spike No More paper, which is all about the magnitude of the embeddings, so we tried some stuff there. Pete Walsh on our team tried some other stuff involving Adam W settings that made things even better. And then we took a lot of inspiration from the Chameleon models, because we were talking to that team on a semi-regular basis, and they had a lot of stability issues. They found some solutions that we also tried, and some of them worked for us, and some of them didn't, and we took the ones that worked for us. Always ablating at the 7B scale until our numbers look super smooth and super nice.
How specific do you think these are to like our setup? Like, are these all OLMo specific insights, or is it just kind of a process you have to walk down? We've heard some of these things before. Is like it's like all these developments are you have to do like the previous type of thing before you can go bigger or do like a more complicated model. Like, do you think that's actually true, or is there just best configurations at the time?
I really don't know the answer to that. And something I want to know, something I want to do for OLMo 3 is walk back a few of these things and see in retrospect which ones of these are actually necessary.
Yeah.
And in particular, I'm hoping that some of those are not necessary and they're costing a bit of performance. To boost our own efficiency a little bit.
In general, I don't know, maybe, you can tell me if there's a useful summary, but it seems like the space of intervention you can take is so big, and how their model, they're not going to translate perfectly, but the hit rate to like find a good solution is higher if you start from that model and you explore around it versus like try to explore like the full space of possible solutions.
Yeah.
And then some things will not pan out once you try to rerun them on your setup. And I don't think that's an indication of like necessarily that we mistakenly re-implement their thing not in the way they're supposed to be. It's more like some things translate, some things don't. But it's a good starting point.
Yeah.
I mean, we are a fairly conservative bunch with this, right? Because even the 7B runs are actually kind of expensive. So we make small changes from a known baseline by and large.
Yeah, I mean everyone has the risk. The risk is pretty obvious when you look at the cost numbers and like who you are trying to beat or not, and it's like we are trying to plat or people can build on it, and it's much better to keep making small progress than it is to go for glory runs and just hope that works. I think most orgs, the more compute you have, you can have a bigger distribution of investments, but it's not that surprising.
I mean, I hope that we can be a lab that is a little bit more risk tolerant than others. For one thing, we don't have Meta's resources, so we should be a little bit more aggressive. It would make me much more nervous if I had to bet $1 billion on our next run than the amounts that we can bet. So we can try a little bit more. I also feel, and I hope that our management agrees with this, I feel that if we're always safe, if every one of our runs works, that means we're not trying hard enough, right? We have to occasionally crash and burn.
I think there's a few every year that you should crash and burn.
Yeah.
I think these crash and burns at the big scale get a lot of attention from media and stuff, but it's like, what do you expect them to do? Like, they haven't, you're walking up a line and might as well like try to take 3 steps at once every so often.
Exactly.
But I do agree. I think that's a cultural thing that we're trying to navigate. It's like, how do we do more interesting stuff and not just fall into the trap of like, be the best open model. No one else is doing this. Like, okay, you could do that for a while, but it's not as motivating.
It's not just because it's more interesting to do that, but also just the fastest way to make a better model. The fastest way to calibrate your risk tolerance properly, you have to sometimes be over. Like,
yeah.
It's inevitable.
Any follow-ups on risk?
Yeah, well, I'm thinking now it's like, because the 70B crash was so sad. For the whole
Yeah, I
team.
mean,
And I'm wondering if you look back on it now, it's like, that was the greatest thing for us. We learned so much from that.
It was
Or
very
it's like,
important to
oh
too.
my God.
I do a little bit. So, I mean, we felt terrible, right? Like, this was an awful time for.
Yeah, it was rough. I was still remote at the time. I was like, I'm not asking any questions.
No, we were the training team that couldn't train a model. I felt so bad. But the work we did following up is some of the proudest I've been about the stuff I've done in my time at AI2.
Yeah, in general, like my thing about like the role of OLMo, sort of it keeps evolving, right? It was very natural to have OLMo as these models designed to help others do research on language models. That's how we initially, it was a big part of OLMo 1. You just like release all the components because it's important to have these tools available to everyone to study language models. And I think we serve that community well. One thing that I hope we can do with OLMo more is that there are like some interesting aspects of language models, interesting capability, interesting architectural decision that for a myriad of reasons they sort of get overlooked in like say a company or like in a framework where you have certain constraints in your model, but they are important. There are questions around like what a model should be able to do, how it should operate, and things like that. That I think we can take a role where like we have in general this recipe that both enables research a language model and for like subset of model capabilities that we think are fundamental, but no one is touching. It's our space to do work there. I think the prime example that I keep repeating these days is what we did with MoMo and pointing. We all had like supporting role for MoMo, and our vision team was mostly working on it. And MoMo is very good vision language model in general. It benchmarks up there. It's not the best, but it benchmarks up there with other models. And then it has this interesting pointing capability that no other vision language model has. And that pointing capability turns out is fundamental for a lot of language models and robotics that you want to build. It's a core capability the same way that a text model should have long context. And it was cool to make sort of emphasize that of like, oh, we have the specific capabilities that would enable all these application, and so more people should work on like the specific aspects. So I think that's a cool way to like work on things that folks haven't had a chance to touch on yet.
I think it's like trying to parse out why this type of situation could happen is not easy, because everybody would want to do this. Like everybody wants to come up with a new capability that expands the scope of what X type of AI model can do. And I think it's most of like probably goes down to the culture of where people have space to think about stuff in a more interesting way. It's like, because obviously everyone wants to have breakthroughs that like OpenAI and dropping that copy. But it's like sitting at a boundary between doing just the same stuff and doing more researchy stuff that you need to have. I have more architecture questions. One is MUP. Multiple people are asking about it. I still don't really intuitively know what it is, but are we going to use this?
We have done a fair bit of work into it, and it hasn't worked for us yet.
Can you explain what it is?
MUP is mainly a way of setting the learning rate, but also some other hyperparameters by training only small models and then having a guarantee, or at least a pretty good idea, that it will work also for larger models. We have implemented this. We've experimented with it. So far in our setup, it works across model sizes. So the learning rate that it predicts you should use is this. It doesn't predict the learning; it just gives you one learning rate. Basically, the good learning rate for the small model is also the good learning rate for the big model. That works if we change the size of the model. It does not so far work if we change the length of the training run. And that's why we haven't been using it so far. Like
number of tokens. It just doesn't adapt to.
Over a longer, if we double the length of the training run, or we 10x the length of the training run, the optimal learning rate is different in our setup. It seems like this might be about. It should work, but it doesn't.
And the positive gain is just have better scaling because you don't have to fiddle with a certain. You're getting the right learning rate, which is a crucial hyperparameter.
Yeah, it's just a better way of setting learning rate, and it works for a few other hyperparameters too. But
Are there open models that use this explicitly?
pretty sure. I mean, open weights model.
Yeah,
certainly.
Like a Llama and stuff using this.
Llama does not, I think, but I don't know for sure.
We'll always see with the next iteration. They're like even Llama 3 felt like they were still building their org and their infrastructure so fast that it's just like get in what you can get in, and there will be more models in the future.
Yeah, I mean, MUP is a shortcut, right? Like you can, for many settings where MUP wouldn't work, you have to just establish scaling laws and predict what it will be. You could do the same thing for the learning rate. Just MUP lets you do this with even fewer runs. You don't even have to extrapolate anything anymore. It just you use MUP and your setting will work. That's the idea. But you kind of already need a scaling law setup anyways for things that MUP doesn't work for, like architecture changes and so on. So in that sense, it's not that important. It's still pretty important, and we're going to keep trying to make it work for us. Maybe just find the bug. But it's not absolutely critical.
How does scaling laws actually tell you the way to change like the width? Do they actually tell you to change the width or the depth, like the proportions of the network relative to the size? Like what are the actual outputted variables? Like, or how are you controlling the architecture you're going to use in the scaling law? Like I know what it's trying to predict the accuracy, but are they on set architecture configs?
You would usually vary one thing.
Okay.
Like you don't vary anything. You establish how it scales with size.
Yeah.
And you set your size according to a certain formula. Like you might say, I will go 1.4x the depth and 1.4x the width, so I have roughly twice as big a model. And you do that a few times, and you draw it on the graph. And then you change your architecture. You do it again. You draw a different graph. You lay them over each other, and you hope that the lines don't cross, and one of them is clearly better than the other.
Yeah, I definitely have known that there's some. It's like what are the obvious things architecture design and the not obvious things. It's like you obviously make the model bigger, but the subtlety of like how tall versus wide. I think we're talking about like I think Clen it's like much deeper than our model architectures, and it's just like as I'm around these things and I don't have an intuition for if tall or wide is better, and I think it's like what works.
There are some early results from Google, I think they're called EfficientNet or something, that suggest that over a wide range, it doesn't matter whether you go wide or deep.
It's not that surprising.
That's pretty old results now. We're following up on a particular result right now. Actually, so OLMo 2 is a 7 and a 13, right? But there also was a 1 that didn't work very well, and we're trying to find out why.
Yeah.
And one thing about that model was it was pretty wide and not very deep. So we're checking whether that is the reason why it wasn't very good.
Yeah.
So we're sort of in the middle of double checking this assumption that it doesn't really matter whether you go wide or deep.
Yeah, that makes sense. I think that is like something that doesn't matter to most people that are probably very interested in. Just like how like there's these blocks and how do they decide? And it's like just one of us decides and it's like seems right.
There are other concerns, right? So if we train with FSDP with 0.3 sharding, so we can try to choose these sizes such that they utilize the GPU in the optimal way. Which has nothing to do with the sort of abstract training dynamics. It's just the practicality of getting the thing into 80 gigabytes of memory.
Yeah.
So then those concerns might take over.
Yeah.
There's other stuff like all your tensor dimensions need to be multiple of 64 or 128, things like that.
GPU math stuff.
Yeah, exactly.
It's really hard to argue against things that are practically making you run fast, because it means that if you find something that's 20% faster, your big run trains fast, all the experimental cycles are 20% faster. So it's not very glamorous, but everyone is really happy when we find one of these like, oh, this is a shortcut. We got numbers
I
faster.
find it super glamour. I mean, when do you ever have such a clear sign of impact that you can say, I wrote this thing and it is now 20% faster?
No, the impact is very glamorous. Yes.
The numbers you're changing are not necessarily glamorous.
Yes.
It's just detailed stuff.
I also think the experimental cycle thing is probably the biggest thing for me. It's what we're seeing consistently is the more experiments you run for a particular idea, the more likely it is to just work out. It's just a function of trying more things. So
It seems like at the pre-training, there's very few, like, you just get the idea. I mean, well, I guess at post-training more, but literally, like, we had a meeting with John Schulman. He was like, everyone, lead labs, train RL on outputs, do this. And we got, like, a 3-month head start on one stuff. But at pre-training, all that stuff, I think, is evaporated.
the human intuition piece is just gone. I think once you do V0, you can kind of do everything with intuition. Like, it's like, oh, look at data. This kind of makes sense. This seems low quality, high quality, etc. And then after you get to like V2 of something, it starts becoming really hard to make sense of what is good for a language model or not. So you kind of just need to just try a bunch of stuff.
And it becomes a game of stacking improvements that are worth 2 to 5% each.
Yeah.
I think it's very compounding, at least in all the math. What works out over a year.
Yeah.
I think I want to ask about MOEs as well, if you have a different thing you want to say. But it's mostly like, it seems like maybe, like we have OLMo, which if you look at the plots on paper, it's like this MOE architecture beats all of our OLMo things and training efficiency. But it seems like we had a path we needed to go down to make sure dense works really well and get all these improvements. And like, then you have to like feed back in, you like merge the MOE streams. We have DeepSeek, we have Minimax, there's countless other MOEs that get really high eval scores. They don't like, they're not as easy to do research with because they have tons of total parameters and people need bigger clusters to fine tune them, blah, blah, blah. But it's like, is MOE something that you think we just need to do to make better models?
Well, it's a complicated question, and we haven't quite answered it yet for ourselves. We did investigate doing a bigger MOE, and we found that the engineering is somewhat difficult. And at the time we came to the conclusion that we could do that engineering, but then who's going to run that thing later? If they also have to have a team of engineers on top of it to make sure they can train this.
What does the engineering look like? It's not like CUDA level kernels, it's how you distribute parameters?
It's a little bit CUDA level kernels in that if megablocks by itself isn't enough for you, then it gets really complicated. And we ran into that situation where if it had to be significantly bigger than what we did, it just got too complicated.
There's like an inference. These very big models that really get advantages by if you tailor them to like where you're gonna do inference with them. So if you're a big company, you start thinking about like how to batch request, how to like serve the model. But if we could do it ourselves for the place where we're running, but then you start thinking like, oh, folks who want to use their model in their hardware, they're better served by a dense model than also redoing this engineering on top. Like there is, I think, a clear advantage if you are also providing an API to do an MOE. It's very clear cut.
It depends on how we think of the product of OLMo, and the number one is still it's an item to be researched. So other people need to be able to train on it and to modify it and so on. And that is just much easier if you have a dense model.
Yeah.
If you think of it as something that gets put into a product, and people will run tons of inference on, and you only really care about the final score that it gets, then maybe the MOE starts making a lot more sense again.
Yeah, that's a good answer. I think it's like, I think people can fill in the blanks on like what we may or may not do, and I think
like different I'm pretty curious like what like folks at Llama, the Llama team think about MOE,
If the AI exists, they're 100% going to do an MOE.
I mean, it's interesting, right? It's like if they're serving few, if they're expecting that the Llama users are going to be, in fact, one of the betters most are few large companies that can figure out inference, then MOE makes sense. But if they're thinking about more like this, it's a model that wants to, it's great if it's adopted by a million developers, large and small, then, they're still going to raise a lot of dense model.
Yeah,
because at the moment it's so easy, so much easier for people to set up their own inference with a dense model.
Yeah, I think we've gone surprisingly long without asking about data. It's like, how much more is it just an infinite hill to climb on data? It's finding good data and filtering bad.
I mean, I think it's an infinite hill to the extent of which everything else is also, and you can kind of keep improving, right? But yeah, it's the main threads constantly are gotta get more data, because if you're working with larger pools of data that you can't necessarily get easily, it's new data that's not in your distribution. It's probably interesting to study how that adds in. And you have more to work from. So if you have like a strict quality filter, you can still get your high token yield if you start with a much larger pool and filter down. So getting more data is really, really critical, especially if you can target specific pockets that you think is missing. You can always keep iterating on better filters, understanding how those filters affect performance, and everything kind of interacts with each other. Like safety filters interact with quality filters, interact with deduplication, interact like all these together. So there's an infinite even ordering search space between these operations. So keep throwing more things at it.
Yeah, it's very much just stacking small improvements.
Shots on goal.
I think the way it looks is like it's for each now that we have like these multiple stages even in pre-training, we think about like what kind of improvement you want to get from data at all the various stages. Like clearly the improvement you want to get from data you put at the end of training is different than the improvement that you want to see at the beginning. It comes with a different set of requirements. One thing that it's really useful is intuitions are always often wrong, but one thing that it's worth spending time on is figure out if you have a data ablation idea, what is the fastest way to disprove it, which requires a little bit of experimental design. And then, you gotta fiddle with like, especially, when you do the first version so that you can take a very, it's very easy to measure improvements. And then as you start thinking like refined version, then, you gotta think of like how you measure your improvements or so. But there's no like big, after you're done, the basic stuff of it, your V1 is done. There's never like a big like thread of like, this is the one data thing. It's more like stacking your Lego bricks to get to a better model.
Do you think you can iterate faster on like end of pre-training, whatever you want to call it, like highest quality mid-training annealing data?
Yeah.
You like started that recently.
I think it depends on what we're getting. We need a little bit more evidence of this, but it depends on the role of data. Like it's very much the reason why we started doing mid-training at all is because we were interested in having base models be primed with certain capabilities that we didn't get during the long pre-training phase. And for those, it's really easy to iterate on new data sources that would improve on those capabilities at the end pre-training. But during like the pre-training phase, one other important aspect that we think about is like efficiency of your data. Is if there is a version of your data set that is where you train on it and the model gets to performance X on 20% faster, it means that you can train for 20% longer, right?
Or run more experiments.
And so, but for those, it's like, it's in some cases you can use mid-training as like a proxy for this. In other cases, it doesn't quite make sense. So you have to come up with like maybe experiments through scaling laws, maybe experiments through some other technique. But it really depends on like what role a data set plays into like the various stages of pre-training.
So it seems like when I compare it to OLMo 1, which is like do the thing, it's all targeted abilities. It's like we want to be better at this. We put people on this. It's like targeted abilities or where we think we can get a lot of data, like a certain data source that hasn't been mined for stuff. Yeah.
We have to be opportunistic because it's so hard to get data. And for us, especially if we want to be open with the data, it's like we have to also do a bunch of due diligence. Like we're going to study this data, put all this effort in, and we're still going to be able to share it with everyone. So
if you were at a lab that didn't release data, do you think you could make more progress on it? Like how much is that actually?
Oh yeah.
oh my gosh, so much time sink that we put in.
Like, and this is not even like doing, getting data that managed are not legal, right? You could form partnership, you have people knocking at our door all the time saying that, do you want to buy this data set? And they're like,
I've been contacted by one ML anon to try to facilitate a data deal.
Oh,
yeah,
on Twitter.
Only the first follow up is like, are you cool if we release that data? Of course they're not.
Yeah, that's what I said to them.
So it's like, it adds, like there's plenty of data that you could acquire from people, but then you can't release it. So that adds a complication to progress.
Yeah, this is more of a self question, but like, how much do you think mid training should be like a philosophical shift in how we organize teams? Because it's very easy to do. I mean, we've already consolidated like our training and data to base, which is not surprising. But this is mostly hypothesizing on what other people do. It's like, how close do you think this kind of end of pre-training to post-training handoff should actually be?
I think it makes sense as a thing I think these things are in theory arbitrary, but you can think of like in the extreme, if you had a perfectly oiled machine, you have a very smooth transition between pre-training to mid-training to post-training, and there's no boundaries. Like that's like a theoretical, you can probably squeeze a ton of performance by smoothing that out. But in real world, stuff is messy. So the real world is your 3 trillion tokens into your base model run, and then you signed a new data deal. You got to do something with this, and you're going to undo your training run. Well, you got to figure out something. So maybe that's mid-training, right? Mid-training is when you have an opportunistic need for something, or you're training something and someone catches a bug, which happens all the time, like a data bug or some training bug. And you're like, okay, well, I had to patch it. So then there's a shift fundamentally. You got to know how to deal with this. So just because these large training runs aren't super repeatable, and they take so much time that the world state changes all the time, you always need some strategy on how to deal with, I'm near the end of pre-training versus I'm near the beginning of pre-training versus...
Yeah, it's like we're obviously trying to solve long context, and this fits right into this. It's like, we're going to do this thing. Does it go? Where does it go? Some people do it in post-training. There's some component during pre-training. It's kind of just like you have to follow a few recipes and figure out what works for your team.
Yeah, and so much of it is just, if it's expensive, try to push it off as much as possible. Because if it's risky, push it off as much as possible. If you can intervene to get the same result much later, huge win. You can try a bunch more things. If you have to intervene because it's some core thing that has to be baked in pre-training time, you're it's a sad space to be in, but then that's the thing that's the pre-training data.
There's a big question that I'd love to get an answer to, but I don't even really know how to think about it. But the question is, what makes a pre-trained model a good candidate for mid-training fine-tuning? Because all we really try to do is we try to maximize our metrics, but we don't really know that those metrics are what makes a good step zero for post-training.
I think a relevant thing, I don't even know if I've told you this, but I don't know how to take action on this, is we got advice that like we have the multiple stages of post-training, and this instruction tune phase, we got advice that's like, it could be a little broken. You can have some crap in there. It'll get fixed later on. And it's like why is that okay?
Yeah.
And like, it might be the same thing in free training. It's like you want to get in the right. It's more important to get in the right ballpark than the right exact number.
Yeah, it feels like it's more about like how to make a good model post training, but what to avoid so you don't have bad model post training.
And yeah, there's a whole other question, which is like how to make a base model that's easy to fine tune in general versus one like if with the right finagling can get the absolute best numbers. Which I think for OLMo would be really great to be like, here's a super stable platform.
Mm-hmm.
So a lot of people, this is like a lot of people have complained about specifically like Llama Instruct is hard to fine tune, which like after most of the post training, because this is where people that have companies start. They're like, this is the best open weight model. I want to add a little thing in it, and a lot of people have difficulty in fine tuning it. It's different at the base because most people can't do this full instruct thing. But for researchers, having a stable platform at base is way more valuable.
There's an interesting about this, like what makes a base model a good base model. There's this interesting, I guess, debate that we've had a bunch of times. We've also had with other people, which is, it seems like there's like two hypotheses on what the role of this, how do you think about data as it affects base model behavior. There's one hypothesis which is you need quality data up so that you don't get any spikes, you have stable training, you have no bugs. And once you pass that level of quality, as diverse as possible. It's just about an init to the model such that it can go in literally any direction. And so diversity spreads. That's one hypothesis. The other one is it's all domain effects. The only reason why, like, you can just keep climbing this notion of quality, but you can keep getting more and more and more as long as you're very clear about what target domain or target application you are. You just keep getting closer.
Well, this is pre-training.
Yeah, well, this goes into like the continued pre-training. It's just domain effects all the way down. If you're only evaluating on this particular stuff, you can always get your base model to be better for that. Just keep climbing on to get it more and more similar. As opposed, and like think about like, I care about this application, this suite of applications, all the way through from base model.
Can you not kind of have both? I feel like I'm confused with how like actual generalization fits into this.
It's competing ideologies in terms of like, if you believe in the first one, then you're all in on diverse data acquisition.
It's like how you set up your team.
Yep, you're all in on efficiency and stability for your pre-training, and then you just get as much different data as possible, and you're post-training all the time. If you believe in the latter one, you solve backwards from this is what I want the model to do, and I make all the changes everywhere to try to squeeze performance out of this class of problem in the data, in the training data, pre-training data, etc.
How important do you think the actual like multi-tag categorization of every data document is? So, like, know that some labs, like that, these people have really advanced tagging of all their pre-trained documents. Like, this is essentially saying like doing that and choosing them, which is like a very much like crafting a like recipe for your pre-training versus like just good numbers. So like just get a good classifier and roll with it.
We have tags.
The tags are useful even if you get this idea of like, let's use as much as possible. Diversity is important. A lot of web data comes with absolutely no useful metadata. You have like what is URLs. URL is very like you have to do things on top of it to make your URL useful. It doesn't add much. So the more you have in terms of like categories, metadata information, you can start using this as a tool to try extra technique on it. Maybe it's extra technique to mix your data in a certain way. Maybe it's filtering out things. Maybe it's like designing benchmarks that try to correlate with those. Otherwise you just need to have this giant bucket with maybe like one quality knob, and it's like, it's very hard to make progress if all you can adjust is like one number we cut for quality here. So I'm not surprised that the big labs, they almost have these tags. I want to know how they use them. That's like the part that's the part that's like
how do you like do this?
Yeah. But it's also not just you have more levers to pull, and then the more things you can try, the better it is. It's also you want tags that are actionable, right? So like if you had a sensible notion of a tag and you realize, oh, more of this data, as you keep adding more of this lever, performance keeps going up. At some point you might be like, we're out of that data. Yeah. We need to go get more of that.
Yeah.
Without that tag, you want that tag to be something that's understandable, so you can go negotiate another deal, do synthetic generation, etc. of that type of thing.
Do you think most of the synthetic data gen is for very specific things at pre-training? I mean, it kind of has to be.
Probably, yeah. You can't just be like, oh, it's generate high quality data. Like that's not something. I don't know what that procedure is, but
it's probably to prime the model to whatever you need during post-training. Like we know we're seeing like normal to with math. It's much better if your model has a rudimentary knowledge of math to like improve on that. And it's quite the same with everything that it's like, oh, I want to do RL on this. If the model is completely random on it, you're gonna have a very hard time.
Yeah, it's like I guess a good transition. It's like, what do you three think post training should be, or like is not doing.
It's elicitation.
That's what I'm coming around to this view that it seems to just you can extract abilities from the model.
I think it's totally elicitation. Like the Hitchhiker's Guide to Data paper from Google. Yeah, that one had like a very specific experiment, but it seemed like that was a pretty strong evidence towards it. It's like if you filter out all of this type of data, you literally can't fine tune that model you can never recover that.
There was hate speech.
It was hate speech detection,
I think
right?
if you do more flops, you potentially can. I mean, it's obvious. Like, we're not talking about like O1 stuff things here, but
Yeah,
like there are even data sets that have like 15 million math only instructions. I think if you like really start doing a ton of math,
At some point, yes.
yeah. But I think that most of it, or it's almost easier to operate on elicitation, which is just like assume that capabilities are in this model, and our post training can get it out.
Sometimes there's this very large set of like things that you do at pre-training because you have a sense of like how they play an application. I think one day is like very obvious. It's like code model. You want them to do completion. You're gonna add fill in the middle loss maybe at the beginning of your training. It's like then you can play my entire pipeline around like that. So it's all about. So far, it seems all about that. Don't think we have cracked a good recipe to do the same for things that are not capability, but they're like recalling facts.
Oh yeah.
Or like long-term knowledge.
Just like it's like all of us like OLMo are like I don't know how these people get their MMLU numbers to go up in X stage. Like instruction tuning boosting MMLU. I'm like, what are you putting in there?
What do you think of mid training then? Is that elicitation or
Mid training is still
causing knowledge?
I think mid training it's still pre-training, but with strong domain effects. It's just smoothing out the boundary between you have a very, very sharp distribution shift when you do post training, and we know from like kind of ML 101 from the past 5-6 years that smoothing out, helping like transition between major domain shifts helps.
But we don't have a clear example of where like it helps with specific knowledge acquisition.
Yes, for that we don't know how to do it, but for like things that are really easy to evaluate, things that are really easy to make progress on, it's like smooth this out.
Well, like, why is post training important to releasing? Like some of you guys came around to like post training being important for getting traction later on. Is that just like an ML ecosystem how it works?
I mean, a base model is kind of useless, right?
Yeah.
Yeah.
It's something.
There's only so many next tokens you need to know about.
Yeah.
But it's like we've seen papers that use OLMo to do research, for example, where the idea from that research only came by comparing base model with instruction tune model. Like the one where folks here were involved around like certain pattern of speech in OLMo 1. Where do they come from? Do they come from pre-training? Do they come from post-training? And like even if you just want to do research, it's kind of useful to being able to compare side by side. So it feels wrong to put a model out that it like cuts sort of the problem that you can study in half till you have the post-training ready. And it's useful to have all in one package so you use it right away.
Post training is just like a really, really long eval loop. Yeah, and that's like, base model, few shot on some benchmarks. Like, no. We eval it by post training it and then evaluating the post training.
Yeah, I mean, to some extent, it is kind of true.
I mean, that's
flying
what we
much
should
more
think
in the
about.
dark if we
could do that cheaply, we would totally hill climb on that metric.
I think that's the metric, because if base model is the good init for the post training, which is the model people actually want to use, then we evaluate it on its status as a good init.
Yeah, so it's like, how do we? And then the question is like, how important do you think research for post training on the specific checkpoint is? It's like how important is genealogy versus like general recipes? Because I think I openly think we under index on using one model, because much like the path to stability, which is a 8 to 10 month really specific thing, I'm guessing if you're really just like in a narrower regime, you can just keep kind of turning these little things.
Yeah.
Hopefully that's something we can do better with new models.
Yeah.
Okay, we kind of go into some wrap up things. how do you think about release decisions? Like, should AI2 release everything that we ever try? Or is it like when should we actually get models out the door?
I mean, I would love to do that actually, especially the failed runs. You know, like where else could you get a repository of failed runs, giving other people the possibility of looking into these failed runs and finding out exactly when they failed? In practice, that's super difficult because just releasing something is hard. You know, you need to upload the checkpoints and translate them in a different format, and you have to describe what you were even trying in some way that makes sense to people outside of the org. Give access to the weights and biases and to the logs, and it's just a lot of work. And there's always something else that seems more pressing than that.
Seems like a scaling, like how much we can share is capped by how we can scale our org.
Mhm.
Which is like we're not going to have a complicated management hierarchy or like an entire org that is just support, and everything you upload you build the support burden. And it's like literally we just see this. We just have seen the envelope grow and grow and grow. It's like more people use our things, you get like more annoying support. Like people want to use it. That's the cost of it.
I guess it's a great problem to have. People want to use that.
And it's more like to make a checkpoint or like some artifact useful, you need the person who was involved. You have Phil, right? You need the person who was involved in it to sort of pour their knowledge into a format that then people can consume outside, right? Otherwise, we would just open up our S3 buckets with a checkpoint, and it would be like actually useless. It's what if you want to know more of the parameters. So like, as long as we optimize for release, that we have the bandwidth to provide like the support around that. If people want the 70V fail run enough, I'm sure we can release it.
It seems like it's just finding the right medium to release things. Like I think long technical reports are really good for the stuff that we do because it just puts everything in one place for people, and it almost makes our job easier in the future. Whereas like we could just drip and drag models out all the time, but like that's not something we can't do. It's just like not in terms of making progress in things that are easy to build on. It's probably just not worth it.
In fact, there's even a cost to it, right? The big example here is we had a release of OLMo 1. OLMo 0724 or July 1.
Yeah.
I think using that for research, that has been probably one of the tougher models because it didn't come with a blog post. It didn't come with like some docs. And so, yes, it's still weights with checkpoints and everything, but comparatively, usually even when people come to us, we're like, oh, we recommend you use 0424. And now with OLMo 2, we're like, oh, that's the one we recommend because it has all the documentation. So just dropping something doesn't seem like it really helps.
I would say we should move faster than the 1 to 2 iteration, but the in between is not necessarily even worth it, which is very odd when you think about being fully open. It's just like kind of with how the costs of doing business.
It's like you want to be fully open, but you don't want to add noise and you don't want to waste people's time, right? So if you drop something that's kind of half done or half baked, and people start spending time on it only to get frustrated later, you've cost them something.
How does this relate to like how pre-training is changing? Like, do you think we need to invest? Like, openly, a lot of startups are changing their relationship to training, and if they're going to use Llama or pre-training or customer data, and we have X compute budget, and does any of this come into play, or is like it's all the same we've been talking about? It's like continue to hill climb, do what you can, make reasonable trade-offs on who will actually use the models. It's like not too different.
I think that for me, the cutoff point is like, is there something useful and generally interesting to add if you pre-train? The case of OLMo, all this like mid-train things that we concluded, we could have not have them. It couldn't be as clean if we started with already pre-trained model. So it's like, is there really something useful to add to the conversation if you pre-train? If we get to a moment when the answer is no, or like diminish in return, I think not adding to the conversation, we shouldn't just create noise for what, like I was saying. But it feels there's still value to add to the conversation, at least in the research side, like pre-training. There is another question of like, we know how to help researchers. We want to help more than just researchers with the models we put out. And if we think there is this application that we can do a very good job, or just this use case is underserved, do a very good job by starting with someone else's pre-trained model, we shouldn't waste compute on pre-training from scratch to solve that. But it's ever evolving question, really. It's like, I don't know, we can make decisions 6 months out, maybe a year.
Well, that's what I would say.
I know you're the pre-training, you're the hardcore, because pre-train some models.
I know there's lots of runway left in food training. The big labs are fairly conservative because they have to be, but that doesn't mean that we're done. I also feel that the point of OLMo is to make pre-training research accessible to more people, because even if you don't have the resources to pre-train the whole thing from scratch, you can still use our checkpoints and use our code to prove out some sort of improvement. And as we've seen in other areas, even Microsoft tries to push .NET, or Apple tries to push Swift or whatever. They try to, it's a really big effort for them, and they try to push this. And the open source community says, I don't care, we're going to use Python, and Python wins. So if you can somehow enable the vast resources of 1 million people banging on a thing, even a company like OpenAI or Meta cannot compete with that. And with OLMo, I'm hoping to capture that a little bit. That if we can capture some of the open source enthusiasm and the academic enthusiasm.
Do you think it'll get better this year? Because a lot of academics are bringing on tens to hundreds of H100 clusters around the country. Like before, it was like just Harvard had 500 and MIT or whatever. But now it's like the long tail of universities. Like there are a lot of people.
I think that makes it a lot better. If you have 200 H100s, you can at least establish scaling laws for your idea. And then, what I'm hoping is someone uses OLMo to try some new thing, establish the scaling laws up to a 3B model or whatever. Then we take it and we prove it up to 30B or whatever our compute allows. And if it still works, then Anthropic and OpenAI take it.
And that's a win. That's not a no. Yeah.
Yeah.
I mean, they would never tell us that they.
It's like, yeah, yeah. What do we need to achieve this? Do we need resources and compute and certain people? Do we need more feedback from the community? Do we need feedback from people at labs telling us which things to do?
Compute and people, for sure. Right? That's undeniable. If you have more computes, you can try more things. We can go bigger, do stuff. If you have more people just trying more things, especially on our artifacts, we'll just learn so much more and not have to just we spend so much time guessworking, trying to piece together things from other people's pieces, and sometimes it's nice to just get something out. They did this on OLMo, we can immediately start working off of it. So people, compute, always for sure.
One thing that we get a lot of feedback that it's I really like AI2, I would like to use OLMo, but it's missing this feature, which is great. I love that feedback because it helps us a lot in prioritization. If we could get more, I would love to also get aspirational feedback of none of the models is doing this, but I have a good case for this. Those to me are always very inspiring to read. But if we'll do it or not, I don't know. It's a question of can we do it and how it butts with other things. But I know those are always very, very welcome.
It'd be really cool. I think what would be really cool is more projects in a space that you can't do unless you have some sort of fully open constellation of artifacts.
Yeah, the thing that Dirk is. Did anyone ever do the thing where you load the model into one GPU and iterate through the batches to find the one what happens when it blows up or when a launch happens?
I mean, to some degree, we did this ourselves.
Yeah. But it's something that people can do.
It's sort of a one-off effort. It's not like we wrote a paper about that. But yeah, I would love to see a detailed write-up of millisecond by millisecond what happens in the retensor when a loss spike happens. How does it actually happen?
These are the things that people can do, and it's you just have to keep zooming into a specific level of details in what happens.
Yeah. I mean, right now we're having someone is using the various checkpoints to see how a certain metric that we're interested in develops throughout pre-training.
And it's
Like
like
you can do that with fairly minimal compute. You don't have to be AI2.
yeah, it's like one of my favorite weird language model papers. It's the Sanderland fishing for magic carp paper. And it's like you can get much more actionable feedback looking at weird tokenizer impacts and tokenizer data interactions on OLMo than just pinging API models and figuring it out.
There's a lot of really cool work looking at the checkpoints that we have with the data batches and trying to do something like, okay, let's replay everything between these steps by injecting some different data or manipulating the data between these two checkpoints just to see how it turns to something different. That stuff is
So
really
how big of a fork does it go
Yeah.
to? Like if you add the same intervention, like how big downstream
Exactly.
does it reconverge?
Or early in pre-training versus later in pre-training, same interventions, messing with the data. It's just like that stuff is really cool.
I mean, I think I've complained this about for a long time. Grad students, I think, are a little bit hesitant to go into pre-training stuff because they need to publish 4 papers a year, and it's pretty difficult to do that when your cycles are so long. But on the flip side, it's a bit less busy a field, so less likely to get scooped if the field doesn't change out from under you while you're in the middle of your project.
Yeah, post-training
Not,
research
at least not quite as much as it happens on your side.
It makes no sense. Just like pick something you want to do and people will probably do it, and that's okay.
So I'm hoping that by publishing all of the stuff and making all the checkpoints available in the data and so on, we can enable more people to work in that side as well.
Yeah. Anything else you guys want to add?
Like, comment, subscribe.
OLMo.
Yeah, I think that's it.
Okay, thanks for listening. If you have questions for any of us individually, the Blue Sky and Twitter handles for everyone in this podcast are below, and you can reach out to the general OLMo contact at allenai.org. That's an email address, or we're really happy to help, and we want to keep building this kind of open scientific ecosystem of language models. So all the best. Bye-bye.